Hi, and welcome back again. So, on the previous videos, um, we were talking about uh, operations with matrices. So, we revised it, how to calculate the determinant of a matrix, the inverse of a matrix, and we focusing on how to calculate the inverse of a matrix because we use it um, in transformation equations. So we also have already solved a transformation equation um, and we use inverse matrices to simplify transformation equations. Um, and on the last video, I saw that on this video, we will solve the example 2.15. But before, I wanted to take a step back and work with you a very important concept, which is how to interpret text, which described at the first moment um, a task that a robot is doing. So on the first moment, uh, we don't have the transformation equation, which describes the motion of the robot. So on this example, we have a robot which is going to drill a hole on a workpiece. So based on a text uh, which is given to us, we interpreted this text, and this way we have to be able to write the transformation equation that will describe the motion of this robot, the task that it have to perform uh, to achieve his objective. Um, we already have solved this example, and on the example 2.15, I use this robot as reference to solve it. But before I wanted to work with you the interpretation of the problem. And for discipline of robotics, you will see that we have to be good in text interpretation. Um, so even without the text, um, let's interpret this task of drill a hole on the workpiece. Um, the first thing uh, that we can interpret is this name in the factor. In the factor, it means where's this the tool that is attached on this frame of the robot. Where's this tool is going to be at the end of the task, and we have to pay attention. We always are tracking the whole system of the robot. So the first thing, we have frames, and these frames are all the time being tracking. So we have a universe reference frame, and this frame is the frame that has the coordinates. And based on this reference frame, so again, we have to interpret um, the names, interpret um, the task. So is reference universe or universe, sorry, universe reference frame. So based on this frame, we write transformations for these other frames. So is a universe reference frame. We have the robot frame, which is represented by the letter R. We have the hand of the robot, which is the frame H. We have the piece, the workpiece, which is represented by the letter P, so it's the frame P, and the end effector, which is the frame E. So without even the text, we can, just knowing the task that this robot it has to perform, we can write its transformation equation, which is the motion that this robot it has to do in order to perform, to active this task. So another thing that we have to pay attention is that we have two bodies right here. We have the robot body, and we have this workpiece, and they are separated. So we already can write a transformation, which is a path, one of the paths that we can do in order to active the point that the end effector will be at the end of the task. But let's do step by step. What is the task that this robot it has to perform? Is to drill a hole on this workpiece. So what we wanted to know is the localization and the orientation of the end effector. In this actually we wanted to know the position and the orientation. And this is resumed as the localization of the end effector, localization of the end effector. Whereas the tool is going to be at the end of the task. So the transformation is the transformation of the end effector in relation to the reference frame U is the transformation of the frame E in relation to the frame U. And this is the first transformation that we can write, just interpreting the task of this robot that this robot it has to do, it has to perform, which is based on this reference frame, because we wanted to know its position and orientation all the time. We are tracking these informations, which is passed to a matrix. And on a real application, we pass these matrices, which contains the coordinates of the position, orientation, to a controller. And now, what is the paths that this robot can do in order to be on this point with certain position and orientation? Well, now if we are working with more precision, so we will have matrices that this robot will use as reference to achieve this certain point. But now let's say we wanted to know the localization and position of the piece without any precision. So we can write that we can know the path of the end effector, which is going to be the same as where this piece is localized. So where's the end effector? And again, the end effector, it means where's the tool which is doing this task is going to be at the end of the task. Is going to be at the same position, at the same localization as this workpiece. So we can write, which is one of the paths which is separated from the robot. And we will write another transformation for the robot as well. So the first transformation, the first path, there are two. The first path is through the piece itself, the workpiece. So we can write the transformation this way. The transformation of the piece, the transformation of the frame P in relation to the frame U. So the end effector is going to be localized at the same localization as the piece without any precision, because we are just writing a transformation equation that describes the motion of this robot, and we are not being precise. And we also can have another path that describes the position and orientation, which resumes on the localization of the end effector. which is the transformation of the end effector in relation to a reference universe. So right here, um, what we have to interpret is the paths that this robot can do in order to active the task. So again, the position and orientation of the end effector. And end effector, it means uh, the end of the task, whereas this tool attached on the end effector is going to be localized on the end of the task. And as we are not working with precision, we are not working with matrices, uh, let's ignore this point and says that the end effector is going to be at the same position and orientation which resumes in on the localization of this workpiece. Okay, and this is one of the paths, and the other path is just right here, the order of the transformations. We don't have a certain order. We can write on the order that we want. They are independently, but we have to track uh, the orientation and the position with this reference frame. So we can write the transformation of the end effector in relation to the reference frame U. The transformation of the frame E in relation to the frame U is how we can know the final position and orientation, where's this tool, where is going to be localized at the end of the task. Transformation of the frame E in relation to the frame U. And now we also can write, we can know the position and orientation which resumes on the localization of the end effector based on the whole system of the robot. You wanted to know this transformation, where the tool that's going to drill a hole on the workpiece is going to be at the end of the task. So first, we can write a transformation for the base of the robot for this frame, which is fixed in relation to the reference frame U. And because we wanted to track the position and orientation, which resumes on the localization all the time. And that is mandatory. Let's say we wanted to know the position and localization, position and orientation of the hand of the robot. which resumes on its localization. We wanted to track this, so we have to write a transformation, reference it to a, a reference system, a reference frame. But right here, what we're going to do, um, these um, reference frames, they these these frames, they turn it in the reference for other frames. So first, we we can write a transformation for the frame R in relation to the frame U, because we are tracking uh, the orientation, the position of this frame R all the time in relation to this reference. Okay, we have to interpretate the names, interpretate the task, uh, the task, the text that is given to us, which described at the first moment uh, the task that this robot is doing, and the names also. So is reference for these frames, and this this frame turn it to reference for this frame. So we are writing a transformation for the frame H in relation to the frame R. This frame is turned to reference for this frame, and we also uh, have to write for as we have 1, 2, 3, 4 links, 5 with the end effector. We have to write transformation uh, to this whole system. We will write a transformation for the end effector in relation to this reference. So this frame turn it to a reference for this frame. So it's a transformation of the frame E in relation to the frame H. Okay? Okay. And as I said on the beginning of the video, we have learned how to calculate inverse of matrices because we use to simplify uh, these equations. So we have a equation, a more clean equation that describes the path that this robot it has it has to do in order to perform certainly task. Um, so you use now inverse transformations to simplify this equation. And now I will write this. I will just change the order right here. Let me copy. I will just change the side. Okay. So you we will cancel this term and this term, so we will be left with only one transformation, will cancel these transformations, and multiplying by its inverse. And what we do on one side of the equation, we have to do on the other side as well. So we can conceal these terms. In this way, we are left with only one transformation on this side of the equation. And now, as we want a equation more more clean, we use some properties so we can get away with these superscripts. They are not exponentials, they are superscripts. So we know now that if we multiply a transformation by its inverse, we will obtain its identity. And also, if we have a inverse transformation, we can write without the superscript by switching the frames. And rewriting the equation without the superscripts. And that's it. How we can write a transformation equation just by interpreting the task that the robot has to perform, or if is passed to us a text, so we interpret this text and write a transformation equation, because this text is describing uh, the task. Uh, and now I think we are ready to solve the example 2.15, which requires from us also a lot of text interpretation, but this we will do on the next video. And for now, I think it's all. Thank you.